Good morning, Oslo. My name's Ian Cooper, and I'm here today to talk to you about Kafka and how you use it as a .NET developer. We'll have both introductory talks about what Kafka is and why Kafka is the way it is, and we'll look at how you'd use it as a .NET developer. We have an hour, so obviously it's not training. I will signpost most of what you need to know, but you'd have to go and dig a bit more to be actually effective. We won't dwell too much on this. I've got a lot of material to get through for only an hour. I'm old, and I encourage you to speak. All of you have content, you just don't know it, right? Anything you tell somebody else is content you could share on a stage. I work on an open source project for .NET developers called Brighter. We are a messaging framework. We compete with things like Mass Transit, Wolverine, and Service Bus. We are particularly good for Kafka because we have what's called a reactor pattern, that is a single-threaded message pump, which means we guarantee and preserve ordering, and we scale in a similar way towards Kafka, which Kafka does. So of all the messaging frameworks out there, we are the one that addresses Kafka most directly. Okay, agenda today is we're going to talk about Kafka. I'll give you a feel for what it is. We'll talk about Kafka and C#, so a broad introduction to working with Kafka and .NET. We'll dig a little under the hood, so we'll learn some things about how Kafka works, and knowing that, we'll then talk about how to make our Kafka code reliable, both as a producer who sends messages and a consumer that reads them. Hopefully we'll have time to cover the last point, which is serialization and schema management around how you're serializing your messages. We'll see how we do for time. Okay, let's talk about Kafka. So Kafka comes out of LinkedIn. There are many surprising things about LinkedIn, including the way that it seems to have become the replacement for kind of X for detailed social media posts in the tech sector. But perhaps more surprising was it produced a significant piece of our infrastructure. So it's created by Jay Krebs, Neha Nakadi, and June Rao in 2011. It became an Apache OSS project in 2012. Most of those people now work at Confluent, although other providers of managed Kafka, such as Avian, are also available. The original use case they were trying to solve was that LinkedIn wanted to fill its data lake with data. They were in data engineering, and they noticed that throughout the organization, they had many bespoke ways of taking data from a source and getting it into their lake. And they asked the question, couldn't we have just one way of doing this, and a way that would support near real-time data being pushed into our data lake? And the solution they came up with was based around the idea of an append-only log, which is an extremely efficient way of writing data. If you can write data and then that data is immutable, nobody will ever try and change that record that you've written to the file, then it's really efficient to just write by adding new items at the end of the log, and all the readers read all these immutable records. So that's what Kafka does. We have a producer, and the producer appends to a log, and we have a consumer, and the consumer reads from that log. Because we write to a persistent storage of format, these two operations can be separated in time. In other words, the producer and the consumer don't have to be available at the same time to succeed. That is what we think of as an asynchronous conversation, right? So WhatsApp on your phone is an asynchronous conversation. You and the other person don't need to be there at the same time for it to succeed. You and I think of asynchronous conversations mediated by some kind of storage as messaging, right? That's the term we just use for that, okay? So Kafka is effectively a messaging solution, but it's very different to something like RabbitMQ, which is a queue. This is a string. All right. So when you and I want to basically use Kafka to communicate, we do so via a topic. A topic just means a topic of conversation. We want to agree that we're going to talk about something that you might be interested in, right? So what do we do for a topic? So a producer writes a record to a topic. A record consists of two things, a key and a value. We'll come back to key a bit later, but the value is essentially the data you want to exchange. It can be in JSON, it could be in protobuf, which is Google's serialization format, And it can also be an Avro, which is a native Kafka format. You don't have to use any one of those. You can use any one in particular that you like. Okay. So the producer makes a TCP/IP connection to your broker. We'll talk more about brokers and clusters a bit later. And it writes to that topic and effectively it appends to that topic. Right? You don't delete records. It's append only. They will basically have a time to live and effectively end up being deleted from the topic, but your code does not delete them. Okay. Your consumer then reads from that topic. So it reads these immutable records, effectively reads them off, you get the value out, and you do something with the value. So you agree that you want to basically be part of this conversation about a topic. A consumer is a single-threaded operation. You want to be able to read sequentially. So Kafka will preserve ordering for you, and ordering may be important because you may want to exchange information about, say, a restaurant or a menu in my current field, and you may want to make sure that effectively that is versioned, and when you read them in order so that you don't get inconsistencies. All right? You can't do sequential unless it's just a single thread. You have multiple threads, things will be out of order. So you can only have one thread reading from a topic in Kafka. Okay. When you've read something, you don't delete it. It's not like a queue in RabbitMQ. It's an append-only log. You have no write access. You don't delete it. So how do you know what you've read? How do you avoid reading the same thing again? Well, you record an offset. So the offset simply says, what records have I read? And you do that by writing to Kafka. There's a topic called consumer offsets where you write what you've read. Those of you that have done, basic work with, say, a CSV file or a similar structured file format where effectively you read it, right? You're doing the same thing. You're reading a certain amount of data, and then you're recording, hey, I've read that amount of data. And you can actually read a certain distance in by figuring out, I want to start at this offset, and then start reading. Kafka lets you do the same thing, all right? So you may be asking, hang on a minute, Ian, this is not going to work. I have far more data than a single thread could read, especially if you're talking about Kafka supporting a near real-time requirement. How can one thread be fast enough to cope with my workload? So what happens is when your producer is writing a record, there are two things, the value and the key. And we use the key to write that record to a bucket called a partition. We can have as many buckets as we like. They cost money and resources and time, so you don't want more than you need, right? And what you do is you say, okay, key 1, 2, 3 goes to the first bucket. Key 1, 2, 4 goes to the second bucket. Key 1, 2, 5 actually goes to the first bucket, right? So there's an algorithm we use to turn that key into a bucket number. We could be random. If we don't care about ordering at all, we can just randomly assign to a bucket. More usually, we use a thing called consistent hashing. So consistent hashing just says, turn that key into a bucket number, and always turn that same key into that same bucket number. And that means, because all of the writes for that particular key always go to the same partition, you preserve ordering. So for a given upstream, like a restaurant, you might have effectively all of the writes for that restaurant about changes to its details go to partition 1 for the same restaurant, right? And that makes it easy for you to continue to be sequential. So the producer writes to a given partition. A consumer reads then not from a topic, but a partition on the topic. So your single-threaded consumer reads from a given partition. So it continues to preserve what is sequential, and what is actually writing to consumer offsets is its progress reading a given partition on a topic. By having multiple consumers, you can read all the partitions on your topic. Now, actually, an individual consumer can read more than one partition, right? But at most, one thread reads any partition. So you could have 6 partitions and 3 consumers. Each one of those consumers would own 2 partitions to read from. right? Your maximum scale is a number of partitions. I don't have time to go into it today, but there's a way to figure out the number of partitions. That's called queuing theory. So queuing theory roughly kind of says you need to figure out the rate at which work arrives, the speed at which you can consume it, and you have to consume faster than things arrive. It's a bit more complicated than that. It involves what's called a Poisson distribution because we assume work doesn't arrive evenly. And that lets you predict the number of partitions, and usually you'd add a healthy amount of headroom on top. You can scale partitions, but it's not what you want to do all the time. Okay. For your application, you want to consume all of the messages on a given topic. But you might have a situation where you have multiple applications that want to read from the same source. So multiple things might want to know about your restaurant information. So in the field I work in, we have things like search wants to know about all the restaurant data. We have things like things that tell you the availability of the restaurant when it's open that essentially want to know about all the restaurant data. Right. So each one of those consuming applications wants to consume all the data. So this creates the idea of a consumer group. A consumer group says, in this group, all of the consumers work together to consume that topic. I will distribute the partitions across those consumers, and those consumers, which are each a single thread, will collaborate to effectively eat their way through the topic. If I have another app, it gets its own consumer group. Right. So that's what this overall looks like. A producer writes a record to an append-only log called a topic, which is partitioned. It writes to a partition based upon the key of the record. Typically, we use an algorithm called consistent hashing to make sure the same key is always written to the same partition. Your application creates a consumer group, and in it puts one or more consumers, usually up to the number of partitions that you have. The partitions are assigned to your consumers, which then can read sequentially through the topic. The number of partitions you need is based upon the rate of arrival of work and how fast you need to consume it. Consumers write their progress to a topic which records the offset they have in a given partition. All right. I'll give you a moment to breathe while I drink some water. That is Kafka, and that is how Kafka works. All right. Those of you familiar with things like RabbitMQ, SQS, Azure Service Bus, those are queues. This is a stream. It's not something I go into in depth today, but it's a different technology. Queues, you delete work when you've read it, and they have different use cases. All right, let's talk about Kafka and C#. Okay, so in order to avoid just doing hello world, I am going to do a little example where we use the transmogrifier from Calvin and Hobbes. I learned, thanks to one of the people in the front row, that apparently you don't know who Calvin and Hobbes is in Norway. So apparently it's Tommy and the Tiger. So that is the Norwegian version. They have a box, a cardboard box. Calvin can change the dial and decide what he wants to change into, like a worm, a frog, a tiger, a baboon. He changes the dial, he goes into the box, and he is transformed into that creature. Okay? So what we're going to do is create something that lets us say in a CLI, hey, what do we want to be transformed into? We'll set up basically what the details of that are. We'll produce a message via Kafka, and our consumer will read that message, and we'll do the transformation, and we'll spit out the result. It's just more exciting than Hello World. If you do these kind of talks and you've written Hello World enough times, trust me, it gets boring. All right, so how does that work in C#? So here what we have is the producer. So the producer effectively in this, we put inside this dispatcher class. And you can see there's a line basically 7 which says there's a producer builder. That's provided to you by the Kafka client library. And what you want to do is use it to create a producer. And it needs a couple of things. The first thing is that string. What that refers to essentially is the key type and the value type. You can use other .NET types here. This just basically is very generic and works. Brighter under the hood uses string and a byte array in order to allow you to use binary data, but you can use specific .NET type, and we'll see that towards the end. And you need to provide it a config. And the config just tells us where to find Kafka. All right. So there's nothing too interesting there. And then what happens is you can see on line 11, we will use that producer to send a message. And that message is essentially going to consist of our settings name as the key, and the value is the transformation that we want to write. And we will send it to the topic, i.e. the topic of conversation. That's just a string. It's an identifier we need to exchange out of band between both halves. Okay. At the end of that, we will flush. Why do we need to flush, and why do we need to wait for it? When I call produce, the Kafka client does not immediately call the broker. It places it on an internal buffer, and a thread reads that buffer to actually post to the broker, and it will retry for you in an attempt to basically make sure that that data reaches the buffer. So if we exit without flush, there is a danger there is still work on the buffer to be processed. You do get a return value from flush, so if I wanted to do this a bit more reliably, I could check to see how many messages are still in the buffer and just do a while loop until I'd cleared that to 0, and essentially there was no work left to be flushed from the buffer. That means that the producer always works in parallel. You don't have to worry about being async. There is an async version. It's actually slower. How do I consume that message? So similarly, you can see on line 8 here, I have a consumer builder. The consumer builder is what the client offers you when I want to build a consumer with it. Again, what I have is some config, and similarly as well, the consumer is a string, so the key value type that I'm using. And you can see it's very similar. I'm telling it where Kafka is. I'm also telling it what the ID of my consumer group is. Remember we said our consumers live inside a consumer group. So I'm just saying, hey, that's my ID. We won't have multiple consumers in our demos, right? So don't worry about that. When we're doing messaging in a consumer, the key idea is called a message pump. Message pump is essentially a while loop, and what we do is we read work out of basically our messaging system, in this case Kafka, and we say, well, it's got some body which is, JSON or Avro or protobuf. In our case, actually, it's just basically a plain text string here that we're using. And what we need to do is effectively convert that into a type. So we pass in a function to our message pump here called a translator, which is simply going to say, take that body and turn it into a type. The next thing we need to do is say, well, I want to action that in some way, so we're going to pass in our handler, which says, hey, when I get one of these messages, what do I do? We know in our case we want to transmogrify you into your favorite creature of some sort. Okay, and a cancellation token. That just lets us cancel the message pump. All right. So what does that look like? So this is a typical message pump. We are going to subscribe to the topic. So we're saying to Kafka, hey, that's the topic we want to basically work with. And then you are essentially going to consume from that topic. So you're going to say, give me the next record on that topic. If it's out of records, if you've read all the records, your offsets have reached the end, there's no new writes for you to catch up in. You're reading an append-only log, so you get an end of file. So if you get an end of file, usually you just wait, because you're going to sit here assuming more data is going to be written in the future. Then we're going to call that function to translate our data, right? And then we're effectively going to handle it. Use that. Right. So if I look at the, we tied it up just to delete at the end. We hold resources. That is that overall flow for you, just as one file. So you can see essentially in our message pump, we are effectively taking some values and then we're calling them as part of the pump's progress. So to use that, what we're actually going to be doing is passing in a set of values, so our group ID. Auto offset reset earliest here just means if we haven't got a consumer offset stored already, where should we start? And this just says start at the beginning. Okay. And then what we're going to do is basically set up a cancellation token so I can cancel it with a key press. And here is the message pump. So what we're doing here is effectively going to be saying translate the message. So we just create one of our own type of transmogrification, and it's a very simple, we're not doing much serialization here. We're just taking the key and the value off the message and passing them back in. So the things we wrote, this table and the box are just spectre.console. I'm not going to get into that in this talk. I'm just making pretty output rather than using console.writeLine, right? So just making the whole thing a bit prettier. All right, and that is the handler function where we will handle the message that we receive. Okay, and that is what that overall looks like in a kind of single file. All right, so let's actually see that in action. Oops, need to escape that, otherwise it doesn't work. Hello. Okay, just for context, here is the code that I'm about to run. I won't show you the context every single time. This is the producer function and the dispatcher code we talked about, where we're going to produce to that topic this message, and then we're going to flush at the end. That is the program it runs in. Most of this is just prompting code from spectre.console. We're going to basically ask your name, ask for the transformation. We're going to display what work it is you want to do, and then we're going to say basically, do you want to enter the transmogrifier? And if you do, we're going to send the message. Over on the consuming side, there is our message pump, right, where we are essentially saying, subscribe to the topic, find a message. When we get a message, call your translator function. When we have a type, call your handler function. And here, effectively, you can see we're saying, run the message pump, do that simple transformation, and effectively then run our output. So let's see that working. Am I in demo 2? Yeah, look, spoilers. I hope that hasn't ruined it for you, the spoilers. Right, okay, so let's run the program. Okay, so my name is Ian. I would like to be a tiger. Right, and it's saying basically, hey Ian, you can enter the transmogrifier and be a tiger. That only seems so exciting. This is Kafka UI. Many UIs are available for Kafka, commercial and non-commercial. I like this one, others like others, right? But it's useful because what it's going to show us is effectively that we have a topic. Now I have to occasionally refresh here because Docker is occasionally slow on my machine. That's why I'm running Kafka. But here you can see I've now created a transmogrification topic. What I've done for simplicity is I've set this up so effectively it will auto-create the topic with a single partition if I haven't got one. You don't do that in production. In production, you use a CLI and you create a topic with a number of partitions that you need, so you can also recreate in the event of DR. It's handy for me, though, to do this because I don't have to faff around with the command line for you. If I go and look at that transmogrification topic, I can see a number of things about it, right? The main thing I can see is messages. So here is the message that I just sent. It's sitting here, and it's basically saying Ian wants to become a tiger. Its key basically is a string, effectively, and its value, so its key you can see is Ian. That's the name of the person we're doing the transformation form, and its value is tiger. All right. You would obviously have more meaningful keys and more meaningful data in a real application. One of the things you are seeing here is this conversation is asynchronous. I have not consumed it yet. Time is passing. It doesn't matter. My consumer does not need to be online at this point to do any work. That's what we mean by an asynchronous conversation. So I'm going to run my consumer, and I'll read basically any work that has accumulated over there. I want to begin the transformation. Of course I do. And effectively, I have been transformed into a tiger. Can you not tell? All right. Okay, what is Kafka like underneath the hood? Okay, so Kafka effectively is a cluster. We do that for resilience, and we basically tend to have multiple brokers in the cluster. Usually you want an odd number, like 3 or 5, because it will have to do some voting. Your partition is essentially consists of a leader and a number of followers. The followers effectively are a copy of the data in the leader. You write to the leader, your data is copied to the followers. Your followers mainly exist for redundancy. If you lose the node that contains your leader, then essentially one of your followers becomes a leader. From about 2.4, it's possible for you to read from a leader as well, for a follower as well, to distribute the load. Okay. Kafka essentially needs... You have to decide, well, who is going to make decisions about who does leaders and followers? And that is called the controller. To get a controller, we obviously need to decide, well, who elects the controller? It's like, how deep does this go? So Kafka, up until about 3.4, had a dependency on something called Zookeeper. Zookeeper essentially is a set of primitives that let you do distributed systems. And what it let you do was basically try and set a given node, and that node with generally the root value. And by writing that node, it's called an ephemeral node, you would say, let's all compete to write that node. And if we succeed, you're the leader. If you fail, you're a follower. And if you basically disappear because it's an ephemeral node, then that node vanishes and somebody else will try and grab it and be the leader. So Zookeeper was just used for leader election. Since about 3.4, it's been possible to use something called Craft, which is Kafka's Raft, which effectively Raft is a distributed systems protocol for doing leader election, so Kafka can do its own election, which removes the Zookeeper protocol. It's a little bit iffy. You have to do some stuff to alter Kafka. It's a bit more difficult to set up, actually, at the minute. That will probably improve over time. Okay. Key thing you need to understand from this, though, is when I write to Kafka, I have to make a decision about what information I want to get before I consider that done. So if I set ax equals 0, I'm saying, yeah, look, I just talked to the broker, and as long as that communication to the broker, the socket's open, I just assume it succeeded. The problem here is it might fail, in which case you have data loss. It's fast, but you risk data loss. You only can do that if you are willing to essentially lose your data, right? And that may be true, right? So one of the things we have, so I work Just Eat Takeaway, one of the things we have is information about, say, the courier and their journey towards you with your food. It may be okay for us to lose individual messages and for the thing to jump, right? We may not actually care about accuracy. Ax equals 1 says, I know it was written to the leader, and then it comes back. I don't know that was propagated to the followers. That's a reasonable trade-off of speed and security. Because what it's saying is, well, I know Kafka's got it. It's probably propagating it. I don't know exactly if everyone has it. In the event my leader crashes before that data propagates to the other nodes, I will experience data loss. If I'm reading from followers, if I'm using that option, they may also get an inconsistent read. In other words, they may not get the latest values because essentially they may still be on the leader. If you want safety, you have to use ax equals all. It takes the longest amount of time because you write to the leader and it propagates to all the followers, and only then do you get a response back saying you are done. Remember, though, in most cases, your code has moved on, because when you do that produce, you're actually writing to a buffer, and a separate thread is sending from that buffer. It's a single thread, so it preserves ordering, right? So in most cases, you can probably risk all because you're not slowing your program if what you actually need is safety. Kafka has a notion of an instinct replica, so it may be that a given node in the cluster ends up struggling for whatever reason. It's behind a bad network partition. It is essentially died. Kafka uses the idea of latency. How far behind is it when I look at essentially its ability to receive messages from the leader? And at a certain point, it declares it's an out-of-sync replica and takes it out of the cluster. Now, when you write to all, you won't include that node, and you won't be allowed to read from that node until somebody fixes it and gets it back into line, right? And that stops you from all taking forever because you have a bad node in your cluster. Okay. All right, how do we use this information? So we can create a reliable producer by controlling some of these variables. So in that box on the left-hand side, you can see what we're doing here is setting ax to all. We're saying, hey, Kafka, wait until you've written to everything. We're setting retries to 3. So that means the thread in the client that is consuming that buffer of messages you want to write, if it fails to write it once, it will retry 3 times before it gives up. And the retry back off says, how long do I wait between each retry? Maximum in-flight request per connection says, how many threads do I want to use on that buffer? If you require your writes to be sequential, then you can only ever use one. You have multiple threads, you will deorder your writes. So generally, those are a reasonably sensible set of default settings unless you have better information and you know more, all right? So that's where I would start. Okay. So here what we're showing is basically the same producer. Actually, this code is a little bit about saying, look, Kafka lets you set up some things that may be handy for you. We can, effectively from the client, tell it to log errors. We can tell it basically, we can log, we can have an error handler. Okay. On the producer config then is where I set these values. So here you can see basically I'm saying maximum send message retries to 3, max in flight to 1. Enable item potence is useful if you are worried you may write duplicates to that queue. Enable item potence will say, in a given time window, don't let you send something that has the same message ID twice. So it will basically deduplicate for you if you need it. Axe here I'm showing as Axe leader. Axe leader is actually Axe 1. Axe all is probably the one you actually want in most of these cases. I think we did that in the code. Enable delivery reports, we'll talk about in a second. Just note that it's there. Okay. So one of the other things is because this producing of a record to the broker is asynchronous, how do I know it happened? I do producer.produce, my code keeps moving on. It's a background thread that is doing the work of sending from this internal buffer to Kafka. Enable delivery report says, okay, I want you to call me back and tell me whether that operation succeeded or failed, so I will know. So what we're seeing here is a very lightweight version of what's called the outbox pattern. So the outbox pattern says, I want to store information that tells me about successes or writes to the broker. A real outbox would be persisted, and it would effectively engage in a transaction with whatever you're writing to your data store that has an entity. So Brighter or something will do that for you. The code gets pretty complicated. So for the excuse me, for this demo, all I want to do is just have an in-memory outbox so you can see effectively how you would take a delivery report and update the outbox to show that something had been sent. And something like Brighter, what happens is you get a sweeper process that says, hey, is there anything unsent? I should send it. You do risk deordering with an outbox. Okay. We've discussed all that. Okay. This is basically, just out of interest, the whole code. There is an async version, as we discussed. This is just using async to get the delivery report back instead of using that. Oh, I didn't really call that out necessarily. On line 19 is where we add to the outbox the message we're going to send. And on line 22, you can see we're registering a callback handler, which is essentially what we have at line 5. Line 5 is essentially the callback we will run, and all that does is update the value in the outbox. Okay. This is the async version. You can see on the async version what happens is we get the return value from the await, and that is the report. And we would have simply marked status basically at that point. As I say, the async version is actually less performant. Right? It mainly exists because async propagates, and effectively some people like to do that. Okay. Okay, let's demo that. All right. So just quickly, I don't want to frame it all because of time. This code is available online. There'll be links at the end. Here is the dispatcher. And the dispatcher effectively is essentially saying, add to the outbox, produce, call the handler. The outbox you can go and look at later. It's just an in-memory thing. There's nothing sophisticated going on there. All right, the consumer is the same as before. So if I do demo 3, gosh, my IDE, because I've changed the font size, wants to give you all the spoilers, doesn't it? Wow. Okay, my name is, I could be Tommy. because it's Tommy and the Tiger, so why not? And I'm going to become an eel, just for kicks. Tommy wants to become an eel. All right, so you can see what we're outputting here is the information contained in the outbox. So what we're saying is we sent a transmogrification. The status of persisted is what came back from that delivery report. That means effectively Kafka has the information on the axle setting that we gave it. All right, and there's nothing really to see here, but we'll run it just so you can see it works. And you can see essentially that we have now become an eel. All right. All right, tiny bit behind, but we'll keep moving. All right, so what about consumers? So one of the things to note about this consumer, let's look at the bottom comment, that other one's come out of time a bit, is that essentially, so the question is, when do I commit an offset? So if you look in the top box, actually, where it says enable auto commit equals true, and enable auto offset store is true, which is kind of the default. So what we're saying is this. I want to write to Kafka the records that I have read. I'm going to let the client do that for me. The offset store is where effectively the Kafka client that I'm using will hold the offsets that I've read. Auto commit says, I want you to run a thread that every so often flushes those to Kafka to the offset topic. The default, I think, is basically every 5 seconds that will run and flush your offsets. There is a risk, of course, that you crash, your offsets aren't flushed, and you will see work again. Generally, in all messaging scenarios, you should be prepared to see work twice. Okay. The trouble with that here is that effectively, if I fail in the translator or handle steps, I probably don't want to mark that work as done. But if I'm doing this auto offset store equals true, what I'm actually doing is saying, as soon as you read, put it in the offset store and commit it. What I want to do with messaging generally is say, don't actually write that offset until I have done the work. Then if I crash, somebody else will pick up that work. We won't have marked that as being done. So generally, the best technique to do that is to auto-commit and manually store the offset. And this is probably your default. It gets the most help from you for the client and is the most reliable. So what we say here, you can see on line 20, is if that handler returns a success result to us, we will store the offset. And that comes, which passes the consumer result, which is what we get back from Kafka when we read a message, and that contains the offset in it. So we're saying store the offset for us if we succeed. If we fail, we won't store the offset. Someone else will be given the work to do instead of us. All right? So we reset that flag basically to false and do the work. We can choose to also manually commit. We might say, hey, we don't want this default 5-second thing. We'd rather batch up work and send work when we have 10 items or the like, etc. So you can choose to basically say auto commit false and auto offset store false, in which case what you need to do is call commit to say, I want to commit the offset to Kafka at this point. Now, typically, you would actually batch this up, not do it one by one, because that's very chatty. So Brighter, the OSS project I work on, we will actually do this strategy, but what you do is you tell us what is the batch size. We also ask for what's the maximum age, so we will sweep results that basically have been waiting too long to be committed to Kafka. Okay. So manual commit and manual offset storage is okay if you want to take a bit more control of what you're doing. You are assigned partitions. It may be that we decide we have 10 partitions, but in non-peak trading periods, we're only going to run 4 consumers. And, well, let's call it 5, make my maths easy. 5 consumers. So each one of those has 2 partitions. What may happen to us is we say, OK, now we're going to scale up because we're at peak trading, and we're going to go to 10 consumers. So each one will have one partition. What happens then is you lose the partition that you own, and you are reassigned a new partition. There's a thing called sticky. Let's look into sticky. It doesn't really work very well, which tries to avoid this. Everybody loses, everybody gets reassigned. When you lose the partition, right, you get a revoked message. You need to make sure that you've committed any outstanding offsets. This code's a bit naive, by the way. It's quite noisy if you do that, because it will say to you a lot, I've already got those offsets. Why are you trying to commit them again? So generally, you can do a thing where you check and make sure that the offsets basically haven't already been committed. For example, on Brighter, we'll do that for you to try and cut down the noise that it's giving you. Okay. So you need to use whatever strategy you had. So here, one is doing store, and the other is doing basically commit. Okay. So, all right, let's look at reliably consuming a message. We looked at reliably, that word is seeming surprisingly difficult. Reliably sending a message. What about reliably consuming a message? So here you can see in our transmogrifier, we are going to effectively say, we're going to do manual commit. Yay! We're going to basically commit our result. And what we're actually going to do is just write out so we can see it on the screen what effectively we committed. So that will tell us basically we're going to commit this particular offset to this partition on this topic. So, demo number 5 is this one. So let me just do clear and clear. Let's have Calvin. Any preferences for what we transform into? We don't have goose, not an option. Dinosaur. Okay, dinosaur fans have spoken. Dinosaur is complicated to spell. All right, so Calvin is going to turn into a dinosaur. You can see effectively as before, we've got the persisted transmogrification. We'll run that. We'll begin the transmogrification. You can see Calvin has become a dinosaur, but more importantly, don't know why the topic is missing, but we have effectively committed offset 2 to that partition. There's a problem with my code there somewhere. Right. Let's move on. 17 minutes. I think we're okay for time. All right. Serializers, deserializers, and the schema registry. Okay. So, when I write a Kafka record, as you've seen, we effectively can use the kind of plain text value for our value, but more typically, we'll pick one of 3 types of body. JSON, which we all know and love well. Protobuf, those of you that basically work with Google technologies like gRPC will know about protobuf, right, where effectively we define a kind of IDL which describes what the message syntax will look like. And Avro, which is kind of Kafka's native binary type, which essentially lets you describe records and fields on those records. I won't do a full description of Avro in this talk. It would take too long. The main reason why you end up potentially using Avro is one of the strengths of Kafka is its ecosystem. So Kafka has a lot of integrates with a lot of things. Kafka Connect, KSQL, Flink. Those tools tend to be used quite a lot in data engineering in order to shift data around and do transformations on it. Many of those tools depend on a couple of things. One is that you're sending them data in an Avro format, and 2 is that you tell them what the schema of your data is. So to do that, we basically create a schema that describes what to expect in the message body, and we register that with a schema registry. We'll talk about those in a second. Confluent is basically the major provider of a kind of schema registry that you can get. Apiary, I think, is the other one that also conforms to the schema registry API. The schema registry is generally useful, and you can use it in messaging scenarios that aren't related to Kafka for storing schemas and that describe your messages. Okay. This is a thing about schema compatibility. So Kafka wants you to set, in order to check a message that you're going to send is compatible with your client's, your schema compatibility. And this table, I'm sure some of you are reading it, I've got a simple version in a second for you, tries to describe that relationship, right, with lots of forwards, backwards, transitives, and words that basically are a kind of word salad, all right? What does it actually mean? Okay. Backwards means customers who are essentially using a new schema can read messages sent to them on an old schema. Backwards just means last one. Transitive means all of them. Forward means consumers who have the older version can read messages sent by producers who use a newer version. Generally, that's one of the ones we want most of the time. We're upgrading our producer, we're adding some additional data. We want to make sure we don't break any of our existing consumers who are not using that data. Again, transitive just means all, forwards on its own just means the last one. And full both means producers and consumers can, either one of them could be on the last version, we can communicate successfully, and transitive just means, hey, we can talk to each other all the time. There are no breaking changes in this model. Okay. So what happens is, if you want to use this, look at the top part of the diagram, your producer needs to essentially talk to a schema registry. If your topic doesn't have a registered schema, you probably want to create one at that point. And then essentially the schema registry you can use to enforce that relationship and say, hey, you can't send messages here unless you effectively conform to the rules that I have set. Typically, when your client talks to the schema registry, it locally caches the schemas you're using so that if the schema registry disappears for some reason, like maintenance, your producers don't all stop working. Now, I'm a big believer in something called Postel's Law, which basically says be constrained in what you send, be liberal in what you accept. So I don't tend to basically try and check the message as the consumer, but you can, from a consumer point of view, look in the schema registry, ask for the schema of the message you're receiving, and choose to reject it. It's more usually used from a consumer because they are dynamic and they want to understand what is the shape of the message I'm receiving that I'm going to go and write to a data table, for example. When Kafka was first made, Kafka only had records. It had no headers. So when we think about messaging, we quite often think about the body and we think about the header. Headers contain metadata. Body contains actual data. Kafka had no headers until about version 0.11. Kafka wanted to work with schema registries way before it had headers. So where do I put the schema ID in the message? So Kafka's fantastic solution was to mangle the body. So effectively, the first 5 bytes of what you send in the case that you're using a schema registry are a first byte, a magic byte, which basically says what version of serialization we are using. It's never been anything other than 0, right? And the next 4 bytes are the schema ID, which essentially is the ID of the schema that represents the record type that you're sending, and then it is your data. Okay. So if you want to use the schema registry, when you do serialization, you have to be aware of the magic 5 bytes. Typically, Confluent provides what it calls SerDes, which is serializer deserializers, for you for a given language. So for .NET, for example, we can get some SerDes serializers that will serialize our body and insert the magical 5 bytes for us, right? The problem with that a little bit is that these are built on Newtonsoft JSON, not on system text JSON. So you're back at having a dependency on Newtonsoft JSON and NJSON schema, and the latest version of NJSON schema will break your Kafka. On Brighter, we're going to try and fix it, and we'll take control of those first 5 bytes for you in a future release, so you can do system text JSON directly instead, because it's a pain. However, in here you can see what we're doing is we're saying, where is the schema registry? It's a service that lives somewhere. We're going to need some config to identify it. We're going to use a Confluent version of the JSON serializer. You can see the message we're using here is a string, but our body is now a .NET type transmogrification settings, and we are going to serialize in the set value serializer. We're going to tell it how to take the value you have, which would be one of transmogrification settings, and turn it into a body. Notice also that it says async over async. We are using a non-async producer because it's more efficient, but JSON serialization is async, so we have to do async over async, which of course is the problem of I'm doing blocking while over async. It is painful. Again, that's why we're going to try and fix it for you in Brighter. All right. But you have to live with the world, right? So let's show you the schema registry demo. Okay, so this is only really so that you can tell that there's no, nothing up my sleeve. Where is demo 6 hiding? What have I done there that's weird? Demo 5, demo 6, there we go. All right, so the producer is what we care about. The producer in its dispatcher, you can see now we have effectively changed to be a string of transmogrification settings. We're using the value serializer, so we're saying, how are you going to serialize value types? Before we're just doing it manually. And we're saying here, okay, we're going to take that and serialize it to JSON on the wire. The same code as you saw before, but you can see when we produce down here, the message now's value is the transmogrification settings rather than a string. So that's what we're going to send over the wire. And we're going to tell it to use the schema registry config here. The cached schema registry just means it's a schema registry that once you've read the schema will store it in my program so that I don't have to keep calling if it doesn't exist. All right. So demo 6. Wow, the spoilers are rich today. Okay. All right. You mainly care about this side. The other side is what you've seen before. My name is Tommy, and Tommy wants to become a frog. Okay. So what I'm spitting out there is the schema for you, just so you can see it in line. So you can see effectively what I've done is created a JSON schema, and it's telling you effectively that it is an object, it's JSON, right, with properties basically of name and transformation. Okay, and you can see the sent message stuff before. You can see your schemas in the schema registry in the Confluent UI, so you can effectively go there, and that basically is a slightly clearer view of the schema we just created, didn't exist before. And we have a compatibility of backward. Probably forward would be better, but that's just the default that it's going to give me, and it's telling me that is basically the message that I'm sending. If I come over to topics in my transmogrification, then effectively in my messages, you can see now this one has effectively Tommy being transformed into a frog in JSON rather than the plain text values we were using earlier. You can send whatever you want, plain text, right? So if you don't want to use the schema registry, you can just send your own JSON in, right? You don't have to worry about that. Okay. So I can then consume that just so you can see the loop. There's nothing to see here we haven't seen before. I should begin the transformation, and effectively Tommy has become a frog. Obviously, the code in demo 6 for the consumer will recognize that it's doing this transmogrification here you see there's no handler being passed in for basically the transformation, and that is because we have a deserializer on this side. So we set a deserializer to say, I expect that whatever comes in to be a type, and I expect you to deserialize it for me. We also have a key deserializer just saying, hey, the format of the key is UTF-8 in the string, right? That's to complete that work. All right? Okay. 53 seconds. All right. So that is Kafka. We talked about Kafka itself, this thing that comes out of LinkedIn, is originally comes out of data engineering, lets us write to an append-only log, lets us have producers and write to that log, and consumers that read from the log. Consumers are single-threaded, so in order to preserve ordering, so we need to have multiple partitions in order to scale, so that we can have multiple consumers all reading their own partition. Talked about how we did that from C#. There's a C# client. Generally, you get the one from Confluent. We can use a producer builder to create a producer, has a produce method which writes to a buffer, and then it has a thread that reads from that buffer and pushes your work to Kafka. You need to remember to flush. We have a consumer. We tend to run those in a message pump. That's basically an ongoing while loop. We take the body, we do a translation and say, what is that? Right? Kafka will do that for us if we want it to, and then we handle that message. Talked about under the hood, we said typically Kafka is a cluster, right? A number of nodes. We have a leader, essentially, and some followers. We write to the leader. We can read from the leader or the followers. The followers are mainly there for resilience. We talked about reliable producers. If we want to essentially make sure that we've written to all of the nodes in the cluster, which is typically what we want to do, we say all. We can use that fact we've got this thread reading from a buffer to do retries at a certain interval to make sure we've written stuff. We can also ask it to deduplicate if we're worried about duplication when we write. And we tend to really only want one thread writing from that buffer unless we know that we don't require ordering the messages that we're sending. On a consumer, the key thing that we have to do on a consumer is tell Kafka about what we've read. The default will simply tell it that anything we have read without processing it, it will commit those offsets. Generally, we don't want to do that. Generally, what we actually want to do is wait until we've done our work and then commit the offset so that if we crash, something else will pick it up. And essentially, to do that, we have to take control of how we commit, right? You may want to say enable offset store true, typically, and say enable enable offset store false, enable an auto commit true, to say you take care of flushing those commits, but I want to tell you when to write them. You can go more manual, in which case you take control of the commit process itself, and you get into more advanced stuff. You have to be aware of the need to revoke partitions. Okay. We talked about serializers, and we said, hey, Kafka basically can serialize for you into Avro, JSON, and protobuf, and you can effectively check against the schema registry that the work you're sending is not going to break downstream consumers, and you can check as a consumer that you would be able to understand the work coming in, but more typically that's used for dynamic purposes. You use a schema registry, you register both the schema registry, you get auto registration if you want it for something that's not been seen. Often you don't use that in production. Often in production you say, oh, you need to manually register the schema always. You can then use backwards, forwards rules to determine what your compatibility is. But be aware if you do that, one of the quirks of Kafka is the magic 5 bytes that you'll need to insert because the schema ID lives in the body because the standard was created at a time when Kafka didn't have headers. Okay, some links. The sample code is on my GitHub, so you can go and grab it from there. This presentation is also in GitHub, so you can go and grab it from there. There is a longer version of this presentation, one that's not. So there's one Kafka for .NET Devs, there's one Kafka .NET Devs at NDC Oslo. The longer presentation has some material on Brighter and how Brighter basically helps you with Kafka. Other topics we didn't really get into, Kafka Connect. So it's tooling that lets you essentially read from things like data stores or other queues, convert it into a Kafka topic, or write from a Kafka topic to those kind of tools. I prefer what was Benthos and has recently been acquired and become Red Panda Connect. I think it's a better tool. KSQL, the promise was Streams are an inverse database. So effectively, I can listen to them and over a window build a table which you could then query. KSQL has turned out not to be the success I think Confluent hoped it was, because that isn't actually as useful a scenario as you think. Streams applications. So streams applications are when you want to process a lot of data. You listen to data on a topic, and you write to another topic. So you read from one, write to another transactionally. Mostly support for that only exists in Java. There is a C# port. I can't vouch for how good it is. And that is it. Thank you very, very much.